Today's experiment is about moving average filter and derivative filter as a part of Digital Signal Processing Laboratory. I am Shailaja, third year student of Electronics and Communication Engineering. Before going straight to the experiment, let us just know some theory regarding these filters. First one, moving average filter. Moving average filter is a low-pass finite impulse response, that is FIR filter, commonly used for smoothing an array of sample data or signals. How it works is that it takes L samples of input at a time and takes the average of these L samples and produces a single output. And the equation for this filter is given as follows: y of n equal to 1 by L sigma k equal to 0 to L minus 1 x of n minus k. From this equation we can know that as the length of the filter increases, that is the L value increases, the smoothness of the output increases. We will be showing that smoothing of this curve in few minutes. So let us discuss about transfer function of this filter. Before that, we have to understand the difference between transfer function and impulse response. If any of the system contains initial conditions, that is non-zero initial conditions, then the transfer function differs from impulse response from the way it is obtained. Here h of z, that is the impulse response, equal to y of z by x of z. From the previous equation, that is the equation of this filter, we will be getting this h of z after applying z transform. And to get the Fourier representation of this, we have to replace z by e power j omega, and from that we can get magnitude response and phase response. This is magnitude response and phase response plotted using MATLAB of moving average filter. So for different values of n, we will be getting these type of signals, like these type of graphs for moving average filter. And then derivative filter. Derivative filter is a periodic bandpass FIR filter which produces a quantitative measurement for the rate of change in sample data or signal. Generally, in continuous domain, we will be taking just d by dt of the signal to get the differential. But in digital domain, that is that discrete time domain, we will be using present sample and the previous sample to do the derivative operation. So derivative filters, in this experiment we will be learning about first order derivative filter and 3-point central difference. These two are causal filters. So first let us see the first order derivative filter. It is the causal and LTI filter whose output depends on current input and previous input, which shows the causality property of the filter. It is basically used to highlight high slope region of the signal. And the 3-point central difference filter, it is also a causal filter and LTI filter which considers two delay, that is the twice unit delay input sample about an input sample and itself to produce the output. Therefore it is quite more accurate than the first order difference filter. Let us see these equations. First order filter, that is y of n equal to x of n minus x of n minus 1, and the equation for the transfer function is h of z equal to 1 minus z power minus 1. By substituting z equal to e power j omega, we will be getting the phase response and the magnitude response of this filter. And the 3-point central difference filter, the equation representing this filter will be y of n equal to z of x of n minus x of n minus 2. By applying z transform, we will be calculating the transfer function and it comes out to be 1 minus z power minus 2. So after getting the magnitude response and the phase response, once we plot them, we will be getting these two. The blue one indicates first order difference filter and the red one indicates the 3-point central difference derivative filter. So let us go to the experiment questions. First one, choose a filter to smooth out high frequency noises present in the signal. As we have talked before, the smoothing effect is produced by moving average filter. So here we will be going to use moving average filter, and with L value equal to 0.08 times of n, where n is the total number of samples. Here we will be taking 1000 samples, so our L value will be 8. That is, we will be taking 8 samples at a time to do the averaging operation. So first we have given the samples to the board, and we will be getting the output in Y, and we will be taking this factor, that is the float factor, to be 0.008, and int n is the number of samples that can be obtained by size of x by size of x of 0. This is the standard equation to get the number of items in an array independent of what items it is, like integer, float, or a character. So here we'll be using the baud rate of 9600, that is where you can see in the serial begin 9600. This baud rate should be common to both the system and the laptop you are using, that is the Arduino board through which we'll be sending the data. And void loop, this will run forever, like it's a loop forever. So initially we will be taking L samples at a time, and we will be doing the summation, and then we will be going to do the averaging part, and we will be going to print it first, the signal and the moving average filter output. And we will be using this 300, where you can see in serial print lny of I minus 300. This one is to differentiate the two graphs. This will be the graph. One is that blue one is the original PPG signal that is given, and the red one is the smoothed out signal. And the second part of this experiment is choose a filter to emphasize high slope portions in the signal. This is also we have discussed. To emphasize high slope portions in the signal, we have to use derivative filters. So we'll be considering 2 derivative filters here. So let's go to the code. In the code we'll be seeing that first we are going to give the 1000 samples that are obtained from the PPG signal, and we will be initiating 3 arrays, YA, YB and Y, and we will be getting the size of the array, and we will be communicating through baud rate of 9600. So as we use moving average filter many times, let us first do the void one. So we will be creating a function. Here we will be giving an L value. The parameters will be the number of samples, the factor through which we will get the L value, and the samples, and the output will be Y. So we'll be, as I have discussed earlier, we'll take L samples at a time and do the averaging. This code represents the same. So when we will be doing this averaging function before passing that samples into the derivative filter, because there are very high peaks, that is the noise, we have to get rid of that. So the first for loop indicates the first order derivative filter, and the second for loop indicates the 3-point central difference derivative filter. Let us plot these two through another for loop. Here the blue one will be the smooth out signal, that is the moving average filter output, and the red one is the output of the first order difference filter, where the blue one is given as the input to that filter, and the green one indicates the 3-point central difference filter when the input is the blue one, that is the smooth PPG signal. Let's go to another part, which is design a moving average filter with L equal to floor 0.8 times of n to extract baseline drift component of the signal. So now we'll be thinking, what is the baseline drift component? Generally our signal will be at 0, but due to this baseline drift, that is there will be some, suppose you consider a curve and you have a signal like this and you have a curve like this. Your signal will be mounted upon this curve, and this is called the baseline drift. That is, your signal will be like this instead of being flat. So let us now find the baseline drift for L equal to floor of 0.8 times of n. As usual, we'll be going to give the samples, that is the input, and we'll be taking the output, and we'll be finding the size of array which we actually initiated with it, and we'll be communicating to the baud rate of 9600. We already have created the function of moving average. Let us directly use that, and we'll be getting moving average output in y for L equal to 0.008 and moving average output in z for L equal to 0.8. that is the smoothed out one. And we'll be going to take the difference of these two, because both will have the smoothed out thing, but we'll be getting the baseline drift once we do the differentiation part or the difference part. Here from the graph you can see the red one will be the smoothed out signal with L equal to 0.08 times, and blue one is the original signal and the green one represents 0.8 times of n of baseline drift. So the final part of this experiment is find the output of signal processing system which performs first order derivative filter and then perform an MA with L equal to 8 or 0.08 times of n. So first of all we'll be giving signals or samples which acts as input, and we'll be taking the output in y and z, and we'll be calculating the step size in n. Sorry, it's not step size, it's the number of samples. And we'll be going to the void setup. To begin the communication we have to need a baud rate. Here we'll be setting 9600, and the forever loop will be for int I equal to 1, I less than 1000, I plus plus. We'll be going to take the difference first, because in the question it is mentioned we have to first perform the first order derivative filter. So we'll be taking the difference and storing it in y. That will be our intermediate output, and we'll take this y as input to the moving average filter, and we'll be calculating z. We have already created the function, so we'll be directly using the function. So we have to print these using the another for loop. Like this means the input and the intermediate output and the original output. That is the blue one here at the bottom, it indicates the original signal, that is the PPG signal given, and the red one is indicating the first order derivative filter response, and the green one will be the smoothed out ones, that is x, y and z. Thank you.